In our previous video, we discussed the idea of differentiation by first principles, meaning if you have a function f of x, its derivative f of prime of x is going to be equal to as follows: the limit as h approaches 0 of f of x plus h minus f of x over h. Now, using this formula or differentiation by first principles, we're going to differentiate the following examples. So the derivative of f of x equals x squared is going to be the limit as h approaches 0 f of x plus h, which is x plus h squared minus x squared over h. Because x plus h is your input value and your function will output your input squared. Expanding, we will obtain the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. And simplifying this, we're going to get our limit as h approaches 0 of 2xh plus h squared over h. We have a common factor of h in the numerator, so factorizing that, we're going to obtain h 2x plus h over h. And the h's will cancel, obtaining limit as h approaches 0 of 2x plus h. And since h is approaching 0, this function will tend to 2x, meaning the limit as h approaches 0 of 2x plus h will be equal to 2x. The derivative of x cubed by first principles will be the limit as h approaches 0 of x plus h cubed minus x cubed over h. This will equal the limit as h approaches 0 of x cubed plus 3xh squared plus 3hx squared plus h cubed. This is the expansion of that binomial. You can do this in your own spare time, but that will be the expansion. I'll just write it out. So factorizing that, the x cubes will cancel, and you get the limit h approaches 0 of 3xh squared plus 3hx squared plus h cubed all over h. Factorizing the h, we're going to get limit as h approaches 0 of h 3xh plus 3x squared plus h squared all over h. Similarly, the h's will cancel, and we will get the following limits. Since h tends to 0, this limit will tend to 3x squared. Now, what I want you to focus on is a pattern between these two derivatives. The derivative or d over dx, which is the notation for derivative, where d represents a change in, or otherwise delta. So often you can, in maybe physics, you've dealt with writing formulas such as change in height over change in time. This is similar to writing d on dt of h, or dh on dt. So the change, or d over dx of x squared, will be equal to 2x. Okay, so the 2 went to the front, and the coefficient or the power of the x squared term is now 1. So similarly, the derivative of x cubed, or simply change in x cubed with respect to x, so x is the variable we're differentiating with respect to, is equal to 3x squared. So we took the exponent and brought it down to the coefficient of x cubed, and our exponent also was subtracted by 1. This is a pattern that happened between both these functions, and this pattern is called the power rule. The derivative, or d over dx of x to the power of n for any integer n will be equal to, or any real number will be equal to nx and minus 1. This is called the power rule. Now, to put a bit of focus into what d over dx means, if you have d over dx of, let's say, 3x squared plus y, then you would treat y as a constant term, because you're not differentiating with respect to y. The variable you're differentiating with respect to is x, so you would treat x as the function which is changing. Y is not changing, it is always constant. You're only focusing on a frame of reference of x changing. So the derivative of this will end up being, using our power rule, will be 6 or 3 times 2 x to the power of 2 minus 1 plus 0. The reason for that is the derivative of, or d over dx of, any x to the power of, or constant c x to the power of 0 equal to c times 0 times x to the power of negative 1, which is equal to 0 times x to the power of negative 1, which is equal to 0. So you can treat this as another rule where the derivative of any constant is equal to 0. Now, we understand the idea of what d over dx means. It means you're differentiating any function. Let's say f of x is our function with respect to the variable x, and this will be equal to f of prime of x. And if dy on dx simply means d over dx times y, where your function is y, and you can say y is equal to 3x, you simply differentiate 3x. Now that we understand what the power rule is and the constant rule, let's go through a couple examples. The derivative, or d over dx, of 2x plus 1 will be equal to the derivative of, or I'll expand this derivative to show you the additive nature of differentiation, such that the derivative of two different expressions is equal to the derivative of each expression independent of the other one. So this will be equal to the derivative of 2x plus the derivative of 1. You're allowed to do this, there's no problem in doing this. So this will simply equal 2 times 1 times x to the power of 1 minus 1 plus 0, since it's a constant term, which is equal to 2 times 1 times x to the power of 0, which is equal to 2. Now let's differentiate 3x to the power of 6 minus 14x squared. This will be equal to 3 times 6 times x to the power of 5 minus 14 times 2 times x to the power of 2 minus 1. So notice we brought the 6 down and multiplied it by the 3, which will give us 18, and then the coefficient, or exponent of x to the power of 6 will be reduced by 1, leaving us x to the power of 5. Similarly, for 14x squared, we're going to get 28x. Now let's try differentiating d over dx of x to the power of 100 minus 1 over x to the power of 100. We can write the derivative of 1 over x to the power of 100 as x to the power of negative 100. So this will be equal to x to the power of 100 minus x to the power of negative 100, which will equal to 100 x to the power of 99 minus negative 100 times x to the power of negative 100 minus 1, which will be equal to 100 x to the power of 99 plus, because the two minuses becoming plus, 100 x to the power of minus 101. So this will simply simplify to 100 over x to the power of 101, because we know that x to the power of negative n is equal to 1 over x to the power of n. Now let's try a final example. Derivative of 4x to the power of 72 plus 3x to the power of 6 plus 4 plus 7x. So the derivative of this, similar to every other expression or example, we will differentiate each term independently. So the derivative of 4x to the power of 72 will be equal to 4 times 72 times x to the power of 71 plus the derivative of 3x to the power of 6, which is equal to 3 times 6 times x to the power of 5 plus the derivative of 4, which is simply equal to 0, plus the derivative of 7x, which is simply equal to 7. Simplifying this, we will obtain 4 times 72, which is 282, x to the power of 71, plus 18, x to the power of 5, plus 7. Now, let's do one final example, except this time we'll just do it without the aid of separating our derivative. We'll do it as if we're professionals. Let's say we have derivative of x to the power of 7 plus 100 x to the power of 6 plus 3 over x. So the derivative of this will be 7x to the power of 6 plus 600 x to the power of 5 minus 3 over x squared. Now, just to make sure you guys are on track with me, we took the 7 on the exponent and brought it down to the coefficient, and we subtracted the coefficient by 1 and got 6 by our power rule. Similarly, we took this exponent of 6, brought it down, multiplied it by 100, got 600 based on our power rule, and got 600 times x to the power of 6 minus 1, which is x to the power of 5. And then 3 over x is equal to 3x to the power of negative 1. So your intuition should be that this will become negative, because 3x to the power of negative 1 derivative, when you bring negative 1 down, will be negative 3x to the power of negative 1 minus 1, which is equal to negative 3x negative 2, equal to negative 3 on x squared. So ultimately, your intuition with differentiating fractions with your x term, which you're differentiating by in the denominator, should be that the sign of your function will change, meaning if it's positive, it will become negative and vice versa. And the magnitude of your x value's exponent will increase by 1 because it's actually a negative exponent when you write it out as x to the power of negative n, or 1 over x to the power of n. Write it out as x to the power of negative n, it will be negative. So taking away a negative number from another negative number will increase the magnitude or otherwise negativeness of that number. Hence why you get a larger exponent in the denominator. And that is differentiation by first principles, which allows us to discover the power rule. And this power rule, it can be proven by techniques such as proof by mathematical induction, but that is beyond the scope of calculus, and this is the power rule.